Alrighty, I'm Hadrian Da Vinci, and today I'm going to show you guys how to set up RAG on your local machine, no commercial tools needed. We'll first start off by discussing why use RAG, how it works, downloading the LLM models, a PDF file to ingest. We'll create a model file because we're using Ollama. We'll spin up our Docker container, which actually hosts the LLM. We'll register the models, again, because we are using Ollama. We'll create some RAG code, a Python virtual environment via Conda, and then we'll run the RAG code via ingesting and then querying. So first, let's start off. Why use RAG? So whenever it comes to communicating with an LLM, there's this process, this workflow that happens. The first part is input. This is what you query. This is what you put in. There's a processing that happens, right? So your LLM is taking in that query. It's trying to find you the best answer by using essentially a very complex autocomplete. And then you have your output. This is what you get back. The beauty is that you could substantially increase and improve your output by modifying your input, right? And this is done by feeding it a better context. And that's what RAG's all about. Another reason why you'd want to run this locally is because there are no gatekeepers, meaning that there's no one standing in your way. You can query this as much as you want. There's no throttling that occurs. And the third reason is because of privacy. Yes, you may have an agreement with your current LLM provider. However, that agreement may change. How it works. So, pretty much the way how RAG works is that you have two LLMs. You have a chat LLM. This is what you're talking to. And then you have an embedding LLM. The embedding LLM is used to take your text and then convert that into vectors. Speaking of which, I want to talk about embedding. What does that mean? So embedding is where you create some kind of numerical representation for some data. So in this particular case, we're talking about our data, which is input, and we're converting this into vectors. So we can call this vectorization. And then indexing is when you're storing the vectors in your database. It makes it easier to search. For example, I can imagine like you can store vectors in a sorted fashion. So that way, if you're trying to find the closest vector to what you have, they're right next to each other, right? So the third thing I want to talk about as far as like terminology is semantic similarity. And this is a really big concept. So semantic similarity is like how close are two vectors. And this is done by looking at the cosine similarity. And if you have a cosine similarity of 1, that means that these vectors align completely. They're very close. In fact, they are the same. If you have these vectors aligning as -1, that means they're completely opposites, right? So what's interesting about this is that when it comes to LLMs, there may not be a word to represent this particular feeling or vibe, but we still have that representation, right? And -1 means that it's the opposite. And then 0 means that, they're perpendicular. There's really no relationship between two vectors. The next thing I want to talk about are the steps. So this is what happens during RAG. The first step is really ingesting the data, and then the second step is querying the data, right? So let's kind of dive into ingesting. For ingesting, you have a document. For example, it could be a PDF, it could be a website. For what we're doing today, we're going to be looking at a PDF and a website. So that document is vectorized. Before it can be vectorized, the document is split up into a whole bunch of chunks, a whole bunch of tiny chunks. And then after that, each chunk is turned into a vector. And then as far as storing this within your database, each vector gets its own vector ID. And all this is done by your embedding LLM. So when it comes to storing the data, what happens is you have a series of objects. The key is the vector ID, and then the value is the actual data. That is the chunk. So let's talk about querying the data. So querying the data is when you're interacting or asking your LLM a question using that context. So that first starts off by the user submitting a query, and then that query is vectorized. So once the query is vectorized, the DB is going to retrieve the chunks which are closest in semantic similarity to the input, right? So the chunks which are obtained from the DB are the ones that are most related to the query. And after that, after you have these chunks of text that are most related to the query, that is actually augmented into the query. So say you have the query, right? The query gets related material from the DB and then appends or augments that to the actual query. And this is why they call it augmented, right? And then after that, you have your response. Your response is generated from that augmented query, and that is done by the chat LLM. So that's pretty much how the whole process of RAG works, from ingesting the data and then from querying that data. So next I want to talk about the downloading. So for this, I downloaded two models. I downloaded the Quinn model. This is one of my favorite models to work with. You may notice that this model is larger than what I worked with the last time. The reason why is because after experimenting with this, I realized that I really needed to have a really hefty model because using a smaller model just didn't cut it. The answers that I got were not as relevant. So for you guys too, I recommend using a model that's in the gigabyte range as far as size. And then as far as the embedding LLM, I use the Nomic embedding LLM, and this is a very popular one to use. Now you may also notice that this one is larger than what I usually use. I think I used one that was 49 megabytes. This one is 274. And in doing so, you get much better performance. And again, if you guys recall, when it comes to using RAG, our goal is to get a much better output. And in order to do so, we want to feed it good input. In order to feed it good input, we want to make sure that we have our embedding model, which is on point. And that's why I'm using 274 megabytes versus 49 megabytes. So once you have this, you want to place this in a folder. And let's do this now. So you may notice here, this is my folder. I don't have anything here. Technically, I've already downloaded these models because I did this already. But simply put, you go to Hugging Face, you go to files and versions, and then you'll download the 3 gigabyte model, and then you repeat the same process for the embedding. And let's take a look at what it looks like. So this is Quen 2, and we're looking at the 7 billion parameters. As I mentioned, the version that I got was 3 gigabytes, and that's what I ended up using. And then for the LLM, which is used to embed, I ended up using this one. And we'll go to files and versions. And then for this one, I'm using the one which is 274 megabytes, which is right here. So as you see here, I already have my model folder here, and I've actually downloaded these models. Downloading these files may take anywhere from like 30 seconds to 1 minute. All right, next, we want to download the PDF. So what I'm doing here is I'm ingesting data, and you may notice a theme here. I'm actually ingesting data that's related to Gainesville, Florida. So the way how I'm going to do this is I'm going to follow my instructions here. Let me open up a terminal. And okay, so we'll do make directory, files, cd into files, and then I'll do wget with this particular resource here. All right, awesome. So now we have the files located here. And as far as what I'm doing here, again, as far as what I'm doing here is I'm going to ingest a PDF, and then I will also ingest data from a Wikipedia page. So next I'm creating a model file. The reason why we need a model file is because we're using Ollama. And if you're using a custom model that you've downloaded, you have to register this with Ollama. And in order to register your custom models, they're not really custom, but your downloaded models, you have to create a model file. So one thing to note, as I've written here, is that Ollama is simply a wrapper of Llama CPP, which means that when it comes to using files that you've downloaded, you are really restricted to using GGUF files, right? And when I register this, you'll see something very interesting. you'll see that Ollama will actually take these files and then split them up into smaller pieces. The reason why this is done is because it helps to improve the performance. So let's create this file. CD out of the folder, and we'll make a, we're going to CD into our models folder, and we'll do nano, nomic model file. And then we're going to paste the name of our model that we've downloaded. And then we'll do the same for the Quen model as well. So we'll do nano Quen model file, and we will paste the name of the Quen model that we downloaded. And again, the reason why I'm doing this is because I have to register these files that I've downloaded. One of the questions that you may have is, hey, why did I not use the models that Ollama provides? The reason why is because, as I mentioned before, is that Ollama is doing a lot in the background, and I have a lot more flexibility if I simply download the models myself from Hugging Face. And then once I have these models that I want, then I can simply register the models within Ollama, and hence the model files. Alrighty, so going back to here, once you have the model files, we want to spin up a Docker container. Here I have my Docker Compose container, and let me kind of just discuss what's happening here. So there are two containers that will be created. The first one is going to house Ollama, and the second is going to house my database. Here we're using Chroma DB. You'll also notice here that with my Ollama Docker container, that this mounts the models folder. So if you guys recalled that I downloaded two models, I downloaded my Quen chat model, and then I downloaded my embedding model here. So this is going to be mounted within the container. And this is really great because I can reference this from Ollama inside. You also notice that I have this port opened up, and that's simply because Ollama needs to communicate with my Python program that's going to be running outside. With ChromaDB, it's a similar thing where I have port 8000 opened up. All right, so now that I have this, I'm going to create a file called Docker Compose YAML. So nano Docker Compose. All right. And then next, I'm going to spin up my Docker containers with Docker Compose. This D means it's going to be running in daemon mode, so it's going to start up and just run in the background. All right, let me fix this typo and try again. Let's see, configuration file. Oh, typo. All right. I need to rename this. I forgot to put the O here. At least I'm consistent with my misspelling. That's a good thing. All right, let's try this again. Perfect. And I'm going to do a Docker PS just to make sure it's running as expected. Let's expand this. Perfect. So as you see here, we have our Ollama container here. We have our Chroma container here. Perfect. Good. So now that we have that running, next we want to register these models. So I'm going to actually call my Ollama container and then run create, which is going to say, hey, we have this Quen model here in the folder, and I want to split this up into tiny pieces so Ollama can refer to that. All right, so let's run this in our terminal. Perfect. So this was done for the Quen model, and we're going to repeat the same process for the embedding model. Perfect. All right. So now that we have Ollama, which has registered our models that we have downloaded from Hugging Face, the next step is to create our Python code. So as I mentioned before, there are really two steps to this. The first step is to not embed, excuse me. The first step is to ingest. So this is our ingesting code. And then the next step is to query. And let's do that. So I'm gonna essentially just create this file here. I'm gonna use nano. So I'll do nano ingest.py, and I will copy my code here for ingesting, paste it here. And let me kind of just walk you guys through what's happening here. So first start off by loading LangChain and Ollama, and then this references the embedding LLM. And you guys remember how I mentioned that I'm going to be using documents from Wikipedia. So I've chosen to look at some Wikipedia articles about Gainesville, Florida. And then the second article I wanted to look at was about University of Florida. So for those of you who don't know, University of Florida is in Gainesville. So this is all related to Gainesville itself. And then I'm loading that as a set of web docs. And then this is loading the PDF document. So you may notice here that we have the file path here. We have the PDF name that we've loaded. And then we're loading the PDF docs. And then what's cool here is that once we have all those docs, we simply combine them by just adding the web docs and the PDF docs. And then after that, we will start the process of splitting up these documents. So if you guys recall, the first step of ingesting is that we must split the documents into tiny pieces. In this situation, I'm splitting this up into chunks of 500 tokens, and we have an overlap of 50. And then once we have that split up, we will then start the process of ingesting. So this part of the code is actually looking at the chunks of the document text and then creating those vectors, storing that within the DB, right? So it may not look obvious, but there's actually a lot going on here. Here we're declaring that we're using ChromaDB, and here we have the document splits. We have our embeddings here, and that's it. All right. So now that we have our ingest, we're going to create our Python code for the querying. So we'll do nano query.py, and I'm going to copy my code that I've written here. And before I save, let me kind of just go through this real fast. So again, we're using LangChain. Just like the other, we are initializing our embedding LLM and our chat LLM. And then here we're using vector store. So this is telling the code that we're going to be using ChromaDB. And what's happening here is ChromaDB is actually storing files inside of a folder called Chroma. Once we have that DB defined, we're setting up that retriever. And what this is telling the code is that this is looking at the top three closest text from our DB. So if you guys recall that when we're using RAG, we're actually pulling up relevant documents from our DB. And again, this is looking at the top three via semantic similarity. So once we have those top three documents, we will then make a query using the chat LLM. And then here we're using the retriever that we've defined here. And then this part of the code is simply a while loop. So while true, it's taking our input and then it is querying our chat LLM. And then I put this print just to give us a new line, and then it's printing the result from the LLM. So you have to know that this is a super basic interface. This is not like a fancy web browser, but again, this is really cool because we're able to communicate with the document. So I'm going to save this. So once we have the code defined, we will then create our Python environment. So as far as our structure, we have two containers that are running. We have one container that's actually running Ollama. We have another container that's running that DB. And then on the outside of the container, we're creating Python code that will be interacting with the container. In order to run the Python code, I have to set up my Python environment because I don't want to store everything locally. And that's what this is about. I am using Conda for my virtual environment here. I can show you guys how to install Conda in another video. It's really simple. But one of the reasons why I love Conda is because it's really great for scientific purposes. So I'm going to start by creating my requirements.txt file, and I will use the contents here to be installed. So I'll do nano requirements.txt, place the requirements here, and I will save. And then next, I'm going to create my Conda environment. I'm using Conda or Python 3.12. All right, so now that we have that installed, we're going to activate this environment and then install the requirements. So do conda activate mlrag, and then I'll do pip install -r requirements to install the requirements. So this does take quite a while, and I'm going to take a break and then return once all of the requirements have finished. Alrighty, so now that we've finished installing all of our requirements, next we're going to run our Python code. So I have export user agent here because when I ran the code without it, I was prompted to enter a user agent as an environment variable. So that's why I have this here. So I'm going to export this here again, so I won't get that particular error message. And then we will ingest the data. So I'll do Python ingest.py. As you see here with 7 documents. So if you guys recalled, we had one PDF file and then 2 websites. But the PDF file had 5 different pages. So as far as documents, what it's doing is it's considering the PDF a collection of 5 documents. And do keep in mind that for all of these documents, splitting that up into smaller pieces and then turning that into a vector and then storing that into our Chroma DB. So usually whenever this runs, it takes me about 30 seconds to 1 minute. Alrighty, perfect. As you see, it's finished. We have our 7 documents ingested. So next, we are going to query this information. So I'll do Python query.py. All right, so before I write this query, do keep in mind that the model that I have is 30 gigabytes in size. So that's quite large. This particular machine has 16 megabytes of RAM, which is really not much. And we're not talking about GPU RAM. We're talking about just like RAM on a CPU. So it will take about 30 seconds. And, normally if you're using a GPU, it would be a little bit faster, or probably a lot faster actually. All right, so going back to this, we have where is Gainesville located? So I did take a look at the documents that I uploaded, and I think the Wikipedia page had the latitude and longitude off Gainesville. So I'm asking this question. I expect an answer to be very specific. Perfect. So as you see here, it's actually giving us the latitude and longitude off Gainesville. So let's ask another question. Sports. What sports are played in Gainesville? So Gainesville is known for football and home with the Gators, as you guys may know or may not know. So I'm curious to see if within the documentation that was uploaded, if it's able to parse that and to pull that information out. And I do recall that when I looked at the Wikipedia page, I think it had information about Florida Gators and various things. I also uploaded information about University of Florida as well. So I'd expect it to give me something related to that. So here we have, okay, it says in Gainesville, sports played include football with facilities at Steve Spurrier Field, Ben Hill Griffin Stadium, basketball facilities. Oh yeah, UF is also known for basketball as well. Um, okay, so yeah, this is pretty accurate actually. I think this is doing a really good job because this information is within the document. All right, so let's go to another question. We'll ask, when was Gainesville founded? One of the documents that I have here is actually a historical document about the history of Gainesville. So, it has information about when it was founded, the indigenous people. So I'd expect something that is probably this date or something around this time. Let's see what it says. Okay, so it says Gainesville was established in 1854. So I'm curious, if I look at this document and I look at 1854, what does it say? So 1835, 1850, 1854. So it says Alachua County officials moved the county seat from Newmansville to Gainesville. Okay, so I suppose this is when it was founded. Okay, interesting. Pretty cool. All right, let's ask a question. So this next question that I have here, this is actually an irrelevant question. So I wanted to see how it would do, and I was like, okay, let me ask a question which is completely not within that document. I wanted to see what it says. So what is the matrix? None of the documents that I've uploaded have anything to do with the matrix. While this is loading, I want to show you guys the query code, which is what we're calling right now. And I want to hone in on, uh, no, actually, I want to look not at the query code. I want to look at the ingest code because I want to show you guys these Wikipedia sites that it has. So you guys can kind of see what's being ingested. So this is one of the pages that's being ingested right here. And then the other page that's being ingested is this one. So all the information that we're getting should be related to these two Wikipedia pages or this PDF that we have here. All right, so let's see what it says. Okay, so this is based on information provided. There's no mention of the matrix. The text discusses topics such as transportation related to RTS bus system in Gainesville. That is true. That is something that is in Gainesville. Great. So what I liked about this is that when it doesn't know, when it doesn't know what the answer is, when it doesn't have a good answer, it tells you. So it's actually indicating that there's no mention of the matrix. Uh, therefore, I don't know. Great. I'm really happy that's what it's saying. That's what I wanted to show you guys. So, like in summary, I just showed you guys how to do RAG locally. Again, you don't need to use OpenAI. You don't need to use Claude. You can if you want. However, do recall that you are going to be missing out on privacy, and you'll also have gatekeepers as well. Um, and this is running on my laptop. My laptop doesn't really have that much power, but as you see, I'm able to get a response back. So anyhow, again, until next time, take care.